Welcome to paper session number 9 on frameworks and datasets. So my name is Benjamin Wyers. I'm assistant professor at the, okay, we will be online in 1 minute. Okay, so we need to wait a little bit. Okay.
Shall I share my screen again?
Okay, no, sure. I will just restart. So welcome to paper session number 9 on frameworks and datasets. It's my great pleasure to present 5 very nice papers. So I'm not presenting. Of course, the authors will present the papers. We will have 5 papers throughout the session. My name is Benjamin Wyers. I'm assistant professor at the University of Trier, working on virtual and augmented reality in various application scenarios. And before we start, I would like to just mention some organizational aspects. So for instance, that go to Twitter if you like and follow ISMA conference. They post all new and relevant information there. There is also for discussion, and I think that's very important, there's in Discord for each paper a specific channel. So when you have questions to the authors over the conference and at a later stage, you can always post your questions there. That's also true for the Town meeting, which is following up this session. So if you have questions to the authors, they will move to the Q&A room in Town for track A after the session. So just go there and meet them directly. So, and if you're on YouTube and not registered, so just think about to register to the conference and participate in the interactive elements of the whole conference. So everyone who is here, you can use the Q&A tool offered by Zoom. Just write down your questions, and I will try to then pick them and read them out to the authors after the presentations. So that's, I think, enough for the introduction. So it's my great honor to welcome 5 great presenters for the upcoming session. And I think the first person I would like to introduce is Wolfgang Fuhl. He is postdoc in the Human-Computer Interaction Group at University of Tübingen, so also in Germany. His research focuses on fields of eye tracking, machine learning, and computer vision. And I think that is also the major topic of your paper you would like to present today. So it's entitled TI'd over 20 million real-world eye images with pupil, eyelid, and iris 2D and 3D segmentations, 2D and 3D landmarks, 3D eyeball, gaze vector, and eye movement types. So a talk about a very large data set on eye tracking. So please share your screen and start off with your 12 minutes presentation. Thank you very much.
Thank you very much. Yeah, hello, my name is Wolfgang Fuhl, and I'm presenting the paper TID, which is, as said already, a huge data set. And it contains, of course, images for pupils, iris, eyelid from AR, VR, and head-mounted eye trackers from 7 different. So here you can see some videos. On the left side, landmarks. Center is the gaze vector. You can also skip, so you see a little bit more movement. And here are some eye movements. Fixation means the eye is fixated and you attend only one location. Saccade is a fast movement between fixations or between fixation and smooth pursuits, and SM is the smooth pursuit, so you follow an object, for example. In the data set, we have over 20 million images, real-world images. We have 2D and 3D landmarks of the pupil, iris, and eyelids, or surrounding the sclera. We have the landmarks, the segmentations. Of course, we have the eyeballs, which are computed based on a sphere, and the gaze vector. In addition, we also annotated eye movement times, and we did that in a semi-supervised fashion. Otherwise, it wouldn't be possible to annotate 20 million eye images. Here you see it in comparison to others. Below is ours. Here you can see like segmentation, so pupil, iris, sclera. So what is annotated in all those data sets and what we provide. We also provide a lot of images, but not all. We also included the images from NVIDIA Gaze, LPV, and where is it? Gaze in the wild. Also LC BupilNet Excuse, which is already from our group, but I only provided the link and the site, and of course the annotations for the other data sets. So if you use those images, please also cite their paper. We have different kinds of eye trackers, also VR and AR from NVIDIA Gaze. In NVIDIA Gaze, there are no smooth pursuits because it was more like static images, and then they switched like the person. So therefore, we don't have any smooth pursuits in virtual reality or augmented reality devices, but hopefully we can provide more in the future. In total, 7 eye trackers, different sampling rates, different resolutions, so everything which makes a computer vision challenging. Here are some statistics, so how many pupils, iris, eyelids, eyeballs, optical vectors, and different eye movement types we have in the different data sets. Here, for smooth pursuits is a star because in NVIDIA Gaze, there are no smooth pursuits. Here are also the different resolutions and sampling rates. Most of the data sets are totally normal, that there are more fixations than saccades, but for example, in the look eye tracker, this was like a driving task where you usually have much more smooth pursuits. Some statistics here on the left side, you can see some examples. The left image, this row, this is the original image. Here you can see the segmentations of the pupil, sclera, and iris. Here are the landmarks for the pupil, sclera, and iris. And here is the eyeball as the green circle and the gaze vector. Here you see also some area distributions. These are viscoplots. So the area for the pupil, iris, and eyelid. The red crosses here are considered as outliers by MATLAB. And the same here for the pupil position, x, y, and the radius of this is for the eyeball parameters, pupil position. Comes to the next slide, sorry, and the eyeball radius. Here is logarithmic pupil center, and here is the logarithmic centered gaze vector. So for the gaze vector, we put it in the middle on a sphere 180 pixels wide, and plotted it like a heat map in a logarithmic scale, similar to the pupil center, because tracking recordings like the fixations or the smooth pursuits are much longer than saccades. They have a huge center bias, which you will see in all those plots. But it's good distributed, since we usually try to place the camera so we have all the images, not for the gaze vector because we didn't have to do it there, but all of the other images were centered on a 192 by 144 image. If it was too low, for example, for the MKI tracker, we centered this image so we could compute those statistics. Here you see it for the landmark distribution of the pupil, the landmark distribution of the iris, and the landmark distribution of the eyelids. The black stars are the mean position of this landmark over the entire data set, and the colorful heat map is the distribution, again, in logarithmic scale. Here are some baseline results. So we used ResNet 34 and ResNet 50 and made a cross-validation. So we removed one part and used it as validation, like look in MK as one set, then decouplers, gaze in the wild, labels pupils in the wild, and NVIDIA gaze. And then we used separate nets. This is important because if you try this with one net to predict all, you get usually very, very bad results because the pupil and iris, they are independent of the sclera and all this stuff. At least for us, hopefully this data set will lead to networks which can predict all together. And this resource saving, so we don't need a huge GPU for an eye tracker. We used here the pixel divided by the diagonal for the eyelid, iris, and pupil landmarks. For the segmentation, we used the mean intersection over union. This means larger is better, and here lower is better. The pixel divided by the diagonal, we also used it for the eyeball and the radius. And for the gaze vector, we used the degrees, so the difference in degrees. So here again, lower is better. ResNet 50 performs a little bit better than ResNet 34, but yeah, it doesn't bring those huge benefits. But I think this is similar to classification results for ResNet 34 and ResNet 50. One important thing, the license. So all images and all annotations, which we provide directly. So all annotations can be used scientifically and commercially. You can also ask the lobby department of the University of Tübingen. They will confirm that. There are already a lot of companies which use it and which wrote me for the images from labeled pupils in the wild, NVIDIA gaze and gaze in the wild. Please ask the authors or the groups, and also please cite their papers if you use those images. Thank you very much for your attention. Any questions?
Excellent. Thank you very much. Yeah. Any questions? Are there any questions? So there are no questions so far as I see in the Q&A machine of Zoom. So I would like to just start with a question. So what I was thinking about is the first question that came to my mind is, do you use any kind of standard metadata schema for structuring the meta information for the image data, that in the sense of reusability of data and reuse?
You mean like the task and all that stuff which the person performs, or
for instance,
age of the person?
Yes.
The thing is, I mean, for parts of the data we have it, but for the other data sets, for example, we only have what those authors can provide, and they will provide it to people who will use it. We do not have it for all. For example, for the decouplers, we have, because it's from a very, very old study, my professor, so Enkeleda Kasneci, did this study. We also do not have all the information. Like somebody asked me if I can say which subject is in which video in decouplers, but this is impossible. I cannot really find out. I can tell people which videos I can assign to a subject ID, but not for all.
I see. Probably a follow-up question of this is that a closed data set, or do you plan to have certain kind of extensions to it in future? Because I think that's always a very interesting thing, to have a living database, not just a ready box thing.
Currently, I have a DFG proposal to extend the data set. And this is for RGB images, especially for mobile devices like smartphones and everything, because a lot of people wrote me that they are interested in medical diagnosis devices or apps for mobile phones, which is a big market or coming up market, and they have problems with eye tracking. Because in near infrared images, if you don't have the reflections on the glasses, you see the pupil very, very clear. For RGB images, this is not true, because there are always reflections inside. So this, of course, I want to extend it.
Do you think that there will be someone coming from outside and offering you his or her data set? Because that is also very interesting to like create an open larger data set then.
It would be cool, but I only think this may come from other scientific institutes.
Yeah, sure.
I know now 3 companies, and the first question they had to me, why have I done this? I mean, data is so valuable because in the machine learning age, you need annotated data. But I mean, from the scientific perspective, it's important that everybody has the data with the annotations for comparison and all that stuff. But
there are very, very strong pushes in a certain direction to make data openly available, right? So this is a question, of course, a company needs to raise. I understand this, but from an academic point of view, I totally agree with you. It needs to be somehow shareable, open, and also in the sense of reproducibility, which is a very critical issue. You need such data sets openly available in the wild.
Yeah, and also like what I'm searching, for example, or I wrote so many medical departments to get real 3D eyeball recordings because they do it. I know I also already saw and used the device to see inside the eye and to produce the volume, because I mean, I used a sphere, but it is not a sphere. I mean, there are muscles surrounding it, and if you move the eye, the muscle, it is deformed. Yeah. I'm totally sure. But medical stuff is usually, they never provide data.
Yeah, but there's also like the data protection issues, right? Yeah. Gathering data from human subjects and things. Okay, so thank you very much at this point. Oh, there's just a question. Can you give some examples of possible application that use both eye tracking data set and machine learning? That's a question coming from Luis Quintero.
I mean, in the future, every eye tracker will use machine learning, because what you usually have, I mean, we are humans. So every human is different. There will be humans which have some spots on the eyes, and eye trackers will not work there because classical algorithms will, for example, detect the black spots on the skin as pupil, and the eye tracker will not work. The cool thing about machine learning is that you just have to annotate some of the data, retrain it, and then you can use it. The second part, why machine learning will come in nearly every eye tracking device, is it works much better than the classical algorithms. And if you have everything ready to train it, it's very, very, very fast to apply it. And the applications are, I think, nearly all like foveated rendering and so on for VR devices. Yeah.
Okay, excellent. So at this point, I would like to thank you very much for your presentation and for the discussion, Wolfgang. I very appreciate that.
Thank you very much.
And this would bring me to the second presentation in this session. But before I will introduce you, Slavomir, I would like to encourage everyone to write down questions either here directly in the Q&A in Zoom, or also into the Discord. You can also just discuss that later with Arthur there if you do not want to raise questions here directly. Okay, excellent. So at this point, I'm happy to introduce to you Slavomir Tadea. I try to do it correctly. So he is a PhD graduate from the University of Cambridge in UK. And his research interest includes engineering design and virtual reality. And I think he will present a very small bit of this work to us today, entitled Supporting Iterative Virtual Reality Analytics Design and Evaluation by Systematic Generation of Surrogate Clustered Datasets. So Slavomir, the stage is yours.
Hey, thank you for the introduction, Benjamin. I guess you can see my screen now.
Yes.
Okay, so this talk will be a bit different than the previous one. Thank you for the nice presentation. So here I'm going to talk about artificial generation of data sets instead of using existing ones. So I'll be presenting on behalf of myself and my co-authors, Bart Dragdon and Pera Christensen. So I'm going to first give you a short motivation for this work. Then I'm going to describe our generation method, visualization environment that we developed to test it, as well as user studies and the results of those studies. Okay, so as we probably already know, VR is a very promising platform for immersive visual analytics. However, the design space is quite large, and it's very hard to explore with traditional A/B testing. And one of the factors that makes this complicated are the A/B, the data sets used in the comparisons. And so if we're going to use the same data set in each condition, this is going to cause unavoidable learning effect. On the other hand, if we're going to use different data sets for each condition, we're going to have a new uncontrolled variable. So we are thinking about this issue, and we came up with a method of generating cluster data sets that share similar characteristics, but yet are different enough so we can actually test what we want to test. So this allows systematic comparisons in the experiments. Okay, so how we actually generate the data sets. So you see a piece of the pseudocode on the right. You can find it in the paper in more details. Here I'm just going to give you an overview. So we basically need these four things. So we have to determine the cluster's placement, their sizes. We have to decide whether we want them to overlap or not, and to what extent. And then we have to color code them. So here we use the 3D Brownian motion, random walk, etc. And from this, after we generate this tray, we draw cluster's position using Poisson distribution. So once we have this set of candidates for the positions of the clusters, and of course we choose how many of them we want to have. And in this case, there were 15. And then we have to determine the sizes. So for this, we again use the distribution. We use PowerO to actually came up with the respective cluster sizes, and then we generate the clusters using normal distribution. So depending what values for the arguments of normal distributions we are going to use, we can end up with either sparse or more dense clusters. Then we have to determine the overlap. So this can be done in many ways. We choose, in our opinion, one of the simplest one. So once we generated the cluster, we create a bounding sphere surrounding this cluster, and then we calculate the distances between respective clusters. And depending on this distance, we can choose whether to keep this data set or this cluster within the data set or not. Of course, if we don't want to, the procedure is going to regenerate a different cluster. So once we did this, the last step is to color code those clusters. So this is non-trivial problem. We have to take under considerations many factors. So one of the factors is the distance between the cluster, the spatial distribution, limited number of colors that human eye actually can perceive as different, etc. So we also came up with the heuristic methods that take under consideration all of those points. Again, you see a bit of the pseudocode on the right, and you can find the details in the paper. Here you see a sample of the data set generated, ABC. They're all in the bounding spheres, the small green ones, and you also see overall bounding spheres for the entire data sets. So those three were used in the first part of our study. D, E, F were used in the second part. Please remember the difference between B and C. So B is more vertically aligned, and C is more horizontally aligned. Okay, so this is the visualization environment. So as you can see on the left-hand side at A, that we provided the instructions to the user through the headset. On B, you see what the actual user sees. So those are some clusters. So we choose cubes to mark the points within the cluster. Those were interactive. So whenever user was gazing over those points with the crosshair that was in fixed position in front of the user's head. This point highlighted itself, so the user could know if that can interact with this point at this particular moment. And if the user chose so, he or she could double tap on the Xbox controller to selecting the entire cluster by selecting one point. And as you can see in the image C, once selected, the cluster becomes semi-transparent. So we wanted to keep them semi-transparent just to give the users the opportunity to know what has been done before, although we didn't want to cause more clutter or occlusion. Okay, so how the users do this? So we ran a two-part study. We recruited 18 people in each study. We came up with those three row-level tasks after reading many papers. So first one, the simplest one, was finding and select all the clusters. The second one was finding and selecting the biggest and the largest in the number of points. And the third task was to select all the overlapping clusters. So as you can see, the first one, it's quite simple, whereas T2 and T3 requires from the user to actually gain some understanding on the entire data sets and individual clusters. And this is going to be showcased in the results. So regarding the experimental design, you see the table on the right, the task execution order as well as the datasets order. So as you can see, we were balancing for the datasets rather than tasks because we deemed it more important in this particular case. Okay, and we did the same for the datasets D, E, F. So we measured quite a few things. So first we measured task completion times. Here we understand them as the difference between the task completion from the time the scene wrote. Head rotation, so we understood the head rotation as the sum of angles between successive records, so pretty much in each frame from the forward vector from the middle of camera's frustum. And we also calculated traveled distance, which we understood as the Euclidean distance between consecutive points. So what is worth to note here as well, we see that our users on the rotating chair, they use Xbox controller and Oculus Rift. So on the Xbox controller, they could use triggers to move up and down and joystick to move horizontally. So together with the possibility of rotating on the chair, the user could actually move and look into any direction in the 3D space. So we analyzed the data using general linear three-way mixed repeated measures analysis of variance, so ANOVA. And please remember that non-significance does not mean that the null hypothesis is true. Okay, so the first results, task completion times. So we observe no statistical significant effects between the two experiments. However, there were statistical significant differences between the tasks, as you can see on the right hand. And there were differences between task 1 and task 2, and between task 1 and task 3, but we did not observe the difference between task 2 and 3. Again, this most likely comes from the fact that the task 1 was the easiest one. And you can also see how much time the time was log transform, how much time it took for each data set on average. Yeah. Okay, head rotations. So again, we observed no statistical difference between the two experiments. However, we did observe difference between all three tasks. So you can see the difference between task 1, task 2, task 2 second, and task third, etc. There were also difference between the tasks, this is what I said, but also at the interaction between the experiments and the data sets. Yeah, so we do believe this was driven by the datasets B and C. So please look at the plot at the orange and grayish bars, and you're also going to see the error bars. So they do not really overlap for those two datasets. Yes. So again, if you remember what I told you before, it seems that the datasets B was more vertically aligned, whereas dataset C was more horizontally, and those were the biggest difference between those two. Okay, and the last results traverse distance. Again, we did not observe effects between the two experiments. There were, of course, differences between the tasks. Again, between all the tasks, between task 1 and task 2 and task 3. Yeah, and again, as you can see, there were also differences most likely caused by the datasets B and C, but we did not investigate it further on those two particular tasks. We also tested errors, various kinds of errors, which also look similar. So if you want to see those results, please see the paper. Okay, so some final points. So the generative process simplifies iterative A/B testing. This method can be further enhanced. We do hope that this is going to stimulate a bit of activity in controlling for the datasets, and the Python code as well as the datasets ABCDEF can be downloaded. If anything, please don't hesitate to ask me. I can help you go through the code, although it's quite simple, I believe. Okay, thank you. I hope I'm within the time.
Excellent. Yes, thank you very much for this nice presentation. So please feel free to raise any questions you may have. So this is a question to the audience, and as I do not see any questions yet, I would just like to start. And so I have this question in mind, how you address this issue of artificiality, which is not a word, I think. So how do you, so you have artificial data sets, right? So
yes.
In the end, it's a question about external validity of your research you're putting up on this. And I was wondering how you would like to address this, whether you have a plan for this, or probably your research also has a different direction. So probably you can just discuss this with me a little bit.
Okay, it's a very good question. So the whole idea was, so we started to look into experimental design. Yes, and then you have different types of, as you said, data sets. Some will be fitting your case, some will not, etc., etc. And one issue that we saw was, whatever you do, you test, you use A/B testing, it's going to work on this data set, but then they can tell you, well, actually, you only proven that it does work in this particular case. Is there a way of testing on different things? So this was actually the idea of my supervisor. I'm not going to claim it's mine, that we may try to look into this. And my task here was to look, and I looked to many data sets, too many papers as well, trying to figure it out. What can we do there when we want to artificially generate those sets? So random walk, because it's it's fractal, it's semi-similar. You can see it in physics, in stock market, in many different cases was the first idea. Then I spent some time trying to figure it out, how to sample from this, etc. So we spent quite a bit of time in the method itself. I'm not claiming its idea. So the idea was to even test if it even makes sense. Yeah, hence the user studies. 18 people in each. There were 3 conditions, so we end up with hundreds of data samples. Of course, it's not ideal, as you saw the difference between C and B. So there's some things that we have to further investigate and look into it. So we try to, and I think I make this by the end. So the idea behind the paper at the end is to came up with something that is going to allow you to test quickly. Yeah, very quickly. If you just tweak one thing in your design, you can use the same data set or generate new. Like it's going to be generated within 2-3 seconds, maybe yes. And you can test on this your new idea and then iterate quickly. If you use the same data set and you use the same participants, then you only prove that it's going to work on this data set. If you start to switch data sets, then you have this unavoidable either learning effect, or you're going to have uncontrollable variable. So I know it's a bit well, it's more methodological paper in some respects, I guess, rather than what you see typically. It was also, I believe it was also the first thing that I did in my PhD, to be honest.
I think that the other thing which is very nice is that you have the chance to map performance or other kinds of variables you measure with humans in the loop back to characteristics of the data, because these are the parameters you put into the very beginning of your generation process. This is also somehow generating a certain kind of ground truth then, right? So so I in general, I like the idea, of course. However, I think this mapping to real data might be something which would be interesting. Still, do you plan to compare your approach to real data sets?
So I do, but it's going to depend because I just graduated and switched the groups. So it depends if I find, I guess, collaboration on this work. So please write me or contact me. I'm happy to work this with you, collaborate on this project.
Okay, cool.
Thank you.
So any further questions, please go to Discord or follow the authors and presenters later on after the session to the Gathertone room for track A. This brings me to the big thank you to you, Slavomir, for the presentation. And I'm happy to introduce the next presentation, which will be by Nuno Pereira, who is currently located as a visiting scholar at CMU in Pittsburgh, US. And he is in general working on mixed reality and is a professor at the School of Engineering of the Polytechnic of Porto, ISEP in Porto, Portugal, by the way, a very nice city. He will present the paper entitled Arena, the Augmented Reality Edge Networking Architecture. So thank you very much, Nuno, for being here and presenting your work. And please, the stage is yours.
Well, thank you very much for the introduction. I hope you are seeing my slides right now.
Yes.
Okay, good. So hello, everyone. I'm here today to talk about Arena, the Augmented Reality Edge Networking Architecture. And this was work done in collaboration with Anthony Rowe, Mike Farr, Ivan Liang, Edward Liu, and Eric Rivling, all of us at Carnegie Mellon University. So many have imagined a world where we are surrounded by mixed reality experiences. And indeed, you have here just a few fictional examples that, that show some of these visions and some of these ideas. Currently, with having more and more AR devices that are more capable, that are more widely available, we are actually getting closer and closer to realizing some of these visions from fiction. So looking back at these visions, we can actually step back for a little bit and make this thought experiment about what would be the system components that would be needed to be in place to make at least some of this a reality. So we can think of challenges in localizing and display this content, in supporting different applications, interactive applications from different tenants, and having in place, of course, the right security controls. So let's look for a moment into the specific challenges we address in our work, and particularly to create collaborative mixed reality experiences. So the first challenge we try to address is finding content. So imagine this scenario: you are in an airport hall and you have different content that you can see. For example, some advertisements and some information about where to go to your gate. We would like to be able to find this content, and importantly, find images, 3D models, and also the programs that control their behavior. Next challenge is about sharing state between users in real time. So here you see an example of a model where it's being shared between different devices. As users interact with the model, change it, we want to show this state to all of the devices that are seeing that same model in real time. Next challenge would be security. We want to be able to define who can edit, who can manipulate these models, and who can see them. And it is important to have some flexibility on the granularities that we enforce these permissions. And also we want security mechanisms that work with supporting services and also interacting devices like sensors or actuators that might be in the environment, and we want to bring into these applications. Finally, our final challenge would be actually putting this whole system together, allowing multiple parties to create and host content and make it findable. And again, this includes the images, the 3D models, and the code that defines their behavior. So to address these challenges, we created Arena, the augmented reality edge networking architecture. Arena includes location-based content discovery, defines networked entities that manipulate content, to manipulate content user and device I/O with integrated access control, and it can host and execute user applications. All of this across a different number of AR and VR devices. To create Arena, we learned and leveraged many previous works. One important work is AR browsers that falls into this trend of evolving the current web into what some have called the spatial web, where, among other things, we try to make web applications more aware of their surrounding environment. The development of AR browsers has recently culminated in the WebXR specification that allows us to create mixed reality experiences in a variety of devices in most modern web browsers. Native development frameworks, modifiable virtual environments, and PubSub, actually a central piece of our architecture, are all relevant work that we discuss in our paper. So be sure to go and check it out. So let's do a quick tour of our architecture. In Arena, we call a set of content with its behavior a scene. So the first thing users do is to try to find scenes, to find content. And for this, they use a geographic lookup service we call Atlas that provides of the scenes that are viewable at their current location. So as users select the scene to enter, the programs that are required to run the scene are started by a runtime manager. In this case, we are showing that it decided to start programs in the user's headsets and also a chess program, that's the program of that scene. It decided to run it on an embedded computer nearby. So as the chess program starts, it will draw some content, and this will originate messages that, due to the underlying PubSub that we have supporting in Arena, will be delivered to everyone interested in this content. So in this case would be the programs that are in this scene. It's important to have a look at how we represent scenes in this PubSub structure, and you have that on the left side of the screen. The first two nodes is just a reminder that we might have other scenes that are being viewed by other devices. But in this case, we are actually interested in the 3D chess scene, and we can see that it would have representation for the graphical elements. In this case, we only have the chessboard currently, and also topics for user I/O and for programs. So continuing my example, a user could perform a click, and this would, again, due to the PubSub, get delivered to whoever was interested in this information, whoever subscribed to it. In this case, we are saying it's the chess program. And in response, the chess program would, again, update the content that gets updated to everyone. We could also have another program that starts on the user on the right side. And this program would create new content that again updates everyone that is interested in this. And this, as you would be seeing, this would be making changes to what is represented in this scene in the pub substructure. All of these interactions happen in what we call a realm. This is a set of resources such as edge devices and supporting services that are interacting in real time through a local pub sub bus. So let us have a quick look into the detail of a realm. So a realm includes what we call viewer devices, that is devices that will be displaying content. And these are assumed to be running a web application stack inside a WebXR compatible browser. We also have headless devices such as sensors or actuators, and a set of supporting services. And these could be running in edge servers or in the cloud. Common to all of this is the capability of running sandboxed programs that get dispatched inside the realm. And they interact through a pub sub that is supported by a nearby broker. So during the development of Arena, we had several creators contributing with applications. And I have here some examples of these applications that I'll be showing you. The first example is a tic-tac-toe being played in AR between two users, each one with their own device. The next example I have here is a robot application where, as the robot navigates the environment, it shows the results of its sensing of the environment in the scene. This scene is being localized in the real world using the April tag you can see on the upper left corner. The next example is a prototype AR scene editor where you have two users that are editing this scene. You can see the AR view of these two users on the left side. And on the right side, you can see the VR view of the same scene as the users are using the scene, as it would be seen from, for example, a VR browser. Finally, it is easy to feed users audio and video, which actually makes Arena an interesting platform for telepresence. And in this example, we scanned a building on campus, and then we could have users in VR touring this building and meeting other people that would be remote in VR also. Next, we entered the actual building on campus, and with our device, we could interact with remote users that were touring the building in VR remotely. So we've seen an overview of Arena. This is a platform we developed to facilitate the creation of mixed reality applications. It includes important features such as location-based content discovery, implicitly networked scenes with integrated access control, and it can run sandboxed user applications. Finally, we support these experiences across desktop, mobile platforms, and different AR and VR headsets. And of course, these all map well to the challenges we started with. And in the paper, we show the scalability characteristics of the architecture, security overheads, performance across a range of devices, end-to-end application latency, and typical application workloads. So be sure to check out the paper. Finally, we have online an instance of Arena. So you can go to this website, arenaxr.org, and experiment. And actually, we will demo this platform later in the ISMAR competition. So that's all from me. I'll be happy to take any questions, and I hope to meet you later in one of the breaks. Thanks.
Thank you very much for this great presentation, Nuno. So there are questions. So I will not start with mine, but with some coming from Wolfgang Fuhl. So his first question is, has Arena a big network overhead?
So you can see the plots we have in the paper. We studied a little bit of the overhead, but essentially, no. I mean, all that we are doing is messaging across the network of simple attributes, and actually, that is something that you can also improve. We are currently sending these messages as JSON, but you can definitely do some better encoding there. But if you go and look at the performance in the paper, we can actually scale with a single instance up to around 150 users. And this could be easily improved.
Excellent, thank you. So a follow-up question from Wolfgang is, what internet connection is required for a more or less synchronic interaction? So that's, I think, a very specific question, right?
Yes, I'm just pulling up the numbers. We have some numbers for like kind of typical workloads in the paper, in table 1 of the paper, and we can see that we could support up to 125. That's the number we have here in users, and you have also the typical bandwidth that would be used by each one of them.
Okay, so there's another question by Gabo Soros. How is location and co-location of devices done?
Yeah, so we have a number of ways of registering devices in the real world. Currently, one of the easiest ways is to have April tags, and we use these as references. We also have ways of localizing using UWB, and we are integrating other localization systems every day.
Okay, so I would probably have a last final question on this. What are the big next challenges? So you presented the challenges you addressed by Arena, but what are the next steps?
Yeah, so we are now starting to kind of scale up our deployments, and our idea is to have a number of instances of Arena across different universities, for example, and start working on that scaling and how they could be federated together and have some kind of interaction between all of them.
So sorry, that brings me to another question, unfortunately.
Yeah.
Was not the last one, sorry about this. So what does it mean for legacy code? So for AR applications which are out there. So what is the way to get that into this framework?
Yeah, that's another thing that we have been working on. We've been working on some ways of like connecting Unity to Arena, making it slightly easier to build scenes in Unity that you can then export to Arena and have some connection between them. We've thought about also supporting other tools, and maybe in that way have a little bit of a bridging between the two worlds. But yeah, it's not a clear path to go from like legacy to these kind of Arena applications, but we have some ways of making it slightly easier.
Okay, Nuno, thank you very much for answering all these questions, and thank you for your presentation again. I very appreciate. And as Nuno just said, go to the demos, go to the competition tonight and have a look there to Arena and also to all other presentations that will happen there. So this is a very short advertisement, which brings me to the next presentation. So the next presentation will be presented by Mohamed Kari. So Mohamed, please feel free to, yes, there you are, that's good, first step. And please also share your presentation, because Mohamed will present transformer pose-aware object substitution for composing alternate mixed realities. So
Hi.
Thank you for being here, and the stage is yours.
Thank you. Can you see my screen?
Yes, thank you.
All right. So, hi, my name is Mohamed Kari, and today I want to present our work on pose-aware object substitution for composing alternate mixed realities. Today, hundreds of millions of users enjoy exploring augmented versions of the real world on their mobile devices. We imagine a future where users and we can use MR applications to discover alternate realities. For example, consider this road. In an alternate reality, maybe taking place 100 years from now, this exact same road might still exist, but it is not automobiles that pace down the roads, and instead maybe personal hover cars that are used for transportation. And maybe we humans live side by side with robots. How can an MR app compose such a scene? Where are the lanes traveled by the virtual hover cars, and in which direction do they go? Is the traffic light red so that the hover cars need to wait? Where is the sidewalk where the robots stroll along? Obviously, plane detection and camera pose tracking is not enough. Not even highly advanced geometry reconstruction helps us here. Instead, we must ask the question, how can we create alternate mixed reality scenes that are not only physically, but also semantically coherent? As an answer to this question, we present Transformer, a video see-through mixed reality system for mobile devices that performs 3D pose-aware object substitution to create such semantically consistent mixed reality scenes. Transformer operates in previously unseen, uncontrolled, and open-ended real-world environments. As seen here, the transformed scene features virtual objects that assume behavioral and environment contextual properties of replaced real-world objects in their respective settings. All right, so in real time, Transformer takes color images, single camera as the only input, then detects objects on the frame and determines which pixels belong to them using instant segmentation. Detected objects are removed using real-time video inpainting. In parallel, we estimate the poses of the objects in 3D space. Using both the inpainting result and the estimated 3D object poses, we render posed objects of a chosen theme to create the transformed scene. Okay, so conceptually, Transformer composes the virtual scene with the context provided by the real scene. Therefore, let's take a closer look at related work that uses the real scene context for virtual scene composition. DepthLab, for example, by Du et al. From Google, enables high degrees of realism in AR apps by providing a geometric context. While this enables an astonishing variety of highly compelling AR experiences, this is independent of semantics. In this metaphor, DepthLab aims at the world's syntax rather than its semantics. Then, of course, there is superposition-based AR, where virtual objects are anchored to concealed real-world objects. The puppy filter in the Snapchat lenses or Apple and Emojis app are maybe the most popular examples. This entails the restriction that virtual objects must be larger than the real-world objects if you want to replace real-world objects. Finally, there is physicality-aware VR, where the physical environment is an input to the generation of the virtual world. Being in VR, of course, gives maximum freedom in terms of what is achievable between the difference between virtual world and real world, but actually, we don't want this freedom, right? Instead, for our notion of alternate realities, we want to stay in the realm of the real world. We want to keep its structure. We want to keep white parts of its appearance and just transform the real world in some very distinct dimension. Okay. So these areas are conceptually related in that they use real-world context for virtual scene composition. For its pose-aware object substitution, Transformer removes objects from the scene. Therefore, it is functionally, at least to some part, related to diminished reality. More precisely, we diminish all moving instances of a class using only a real-time stream of monocular RGB. However, diminished reality is not concerned with 3D poses. Therefore, let me stress that Transformer is different from first diminishing and then augmenting objects. At the core of Transformer are these 3D poses that bridge diminished reality and augmented reality, and only by these poses we can reuse context and meaning. Our work is also related to scene construction and visual transformation, but please see the paper for this for more detail. So in summary, our contributions comprise the notion of pose-aware object substitution for creating meaningful theme-based alternate mixed reality scenes with virtual objects that assume contextual properties of replaced real-world objects. We also present a camera to display system architecture, implementation, and design rationale for our system as a distributed mixed reality system that adapts, unifies, and integrates a series of 2D, 3D perception architectures that operate in the wild and in real time. And it includes a parallelization architecture employing three-step pipeline parallelism and threefold task parallelism to achieve near real-time operation of the integrated computer vision models at approximately 15 frames per second. Okay, so design and architecture. We first specified a set of design objectives that enable in the wild application. Transformer shall operate on previously unseen scenes without prior preparation of the environment. This also means that we cannot rely on on-site cameras used in room scale experiences. We also aim for real-time execution, usage of a monocular RGB camera only to ensure mobile device compatibility, and rendering on the handheld display rather than on an HMD. So given our mobile device compatibility constraint, we offload inference through all 4 neural network-based computer vision models to a GPU-accelerated host in the cloud. Let's take a closer look at some of these components of the system, starting with the 3D pose estimation. We estimate 3D poses for vehicles and humans. In the case of vehicles, we estimate translation, rotation, and scale of 3D bounding boxes using a CenterNet-based deep architecture by Liu et al. And in the case of humans, we estimate 18 different 3D key points using an implementation by Ozukin and Ajiva based on the architecture presented by Mehta et al. Okay. So then let's get into object removal based on segmentation and in-painting. For object removal, we first segment all relevant objects in the 2D image space and then fill the resulting holes using in-painting. Our in-painting problem is quite different from what we often find in literature because we don't have stationary masks, but dynamic masks provided by the segmentation, right? Then masks are free-form and non-contiguous. We don't have all the frames in advance, as in video in-painting, but can only look back to past frames, and we must operate at high or reasonable frame rates. Therefore, we have adapted 2 different video in-painting networks for Transformer. With VNet, we incorporate a quality-optimized approach at 7 frames per second, and with LG TSM, we incorporate speed-optimized in-painting. You can see these 2 alternatives side by side running here. So left side quality optimized and right side speed optimized. Left side 7 frames per second, right side 15 frames per second. All right. So, okay, once we have removed objects from the scene, we can render virtual objects in their place, and we do this in Unity. So users can choose from a set of curated themes where we map each detected instance to a virtual object class and instantiate a virtual object using the estimated poses on the in-painted frame. In terms of applications, we see 2 different paradigms for Transformer. First, consumptive interaction, where the user takes the role of an observer who explores their surroundings. And second, creative interaction, where the user takes the role of a director, and this director then records a virtual character proxied by an actor. So following this approach, this director-actor interaction pattern, the directing user can capture 1 or more acting users in context to create a transformed scene. This is reminiscent of motion capturing in professional filmmaking, however, has differences you can see in visual appeal, but also in how can take place in the wild and on the spot. All right, so what are the limitations of the system? Transformer does not track the camera pose. Therefore, we currently cannot tell apart object movement from camera movement, but tracking the cameras and objects, world coordinates would be a remedy, and is possible, of course, with today's technology. Of course, pose-aware object substitution can be used as part of a state-of-the-art AR pipeline, which would also then enable physical coherence too. Also, perceptually challenging situations, occlusions, for example, can lead to tracking failures. So perception is something that can always be improved, and we can always get better. We have dedicated our work to handheld displays, but in terms of immersion, it could be interesting to also target head-mounted displays. And finally, we believe there is potential for enriching the themes by including more object classes, maybe animals or even plants, substituting planes, surfaces, right? Planes, for example, the floor, or even including something like audio AR features that emphasize these narratives for the consumptive usage of Transformer. In summary, we have proposed pose-aware object substitution and implemented it with a cloud-assisted architecture under different in-the-wild design objectives. But taking a step back, Transformer heads towards mixed reality experiences that do not only incorporate geometrical, but also semantical information from the real scene context into the composition of the virtual scene. It also showcases the integration of 4 compute-intensive neural networks. With this, we expect to see more research that explores concepts to realize semantics-driven mixed reality, complementary or derived from this work on reusing semantical object settings. Also, we believe that future research can draw on the feasibility of such a cloud mixed reality approach. With this, thanks a lot for your attention, and please find further information under this URL. And I'm happy to take your questions.
Yeah, thank you very much for this great presentation and the very interesting work. So the stage is now open for questions. And I also see that there are coming some in. So I would like to start with the one that just popped up in the Zoom Q&A. So Mattia Colombo is writing, awesome work. I was wondering how, if additional data to RGB images would enhance the precision of the impainted objects. For instance, having LiDAR sensor providing geometry of the surrounding environment as in the HoloLens.
Yes, so agree. I think the main bottleneck, or like one of the main things that would need to improve, or that I see could be most important, is improving perception, right? And I think there are 2 trends now. So with the iPhone, you see there is suddenly a LiDAR sensor embedded. Also, like with HoloLens, we see this. So I think would be useful to do this. On the other hand, we also see this trend to actually don't use as many sensors, and because we can suddenly do it with deep learning, to just rely on RGB. So I suppose both approaches are interesting and valid. To the question, how would that improve? I think that really depends on the precision of the RGB models that we have nowadays, right? So there, in some, especially for 2D detection, LiDAR doesn't help at all. So for the segmentation, this doesn't have an effect. We do need to do the segmentation. Maybe you remember in one of the snippets, there was one arm still somehow not detected. So LiDAR wouldn't help here at all, especially in terms of the orientation of 3D bounding boxes. Maybe LiDAR could help here, but I think actually that more data, training on more data, training on better data, training on more scene-specific data would be maybe a more viable approach, because then again, with LiDAR, you're always restricted to 5 meters, more or less, in terms of distance to the object. And it's often interesting to see objects really in the context, so at some distance, and therefore LiDAR would not really help us here. But I suppose actually this getting better in 3D, like in spatial perception is really key to improving the perception in the system.
Okay, So the next question comes from Wolfgang Fuhl, and he's asking how many GPUs does one device, smartphone, tablet use on the server?
Good question. So we have, I think, for all the mission critical videos that we shot, we actually used 4 GPUs, so 1 per model. But that was, to be honest, also a bit of a software thing, because sometimes it's difficult to locate different models on the same GPU, and suddenly you would encounter like weird problems. So we used 4, but it was possible to also run it on 2 GPUs. So for like in the development phase, we didn't spend too much money on GPUs and just wanted to like put it down. So in the end, I think the answer is definitely 1 model for in-painting. That is the most compute-intensive thing, probably also because there is not too much work in the computer vision community going into this problem. So 1 GPU for in-painting, 3 models can run on the other 3 models, segmentation, vehicles, humans can run on 1 GPU. So 2 GPUs minimum, 4 is better.
Okay, so this brings me to a last question from the chat. Does Transformer rely only on 2D RGB images or also on depth data available in newer mobile devices?
Exactly, 2D RGB monocular camera images only.
Okay, so that also was quite related to the first question, right? So,
right, yes.
Okay, so if there are no further questions, I can't spot any. Then I would like to thank you very much again for your presentation, for this great work you presented here. And please be reminded that you can find Mohammed later in the Q&A room in Gathertown. Thank you very much.
Thank you so much. Looking forward to meeting you there.
Great. So this brings us to the last presentation in this session on frameworks and datasets. This will be presented by Luis Quintero. He is a PhD student in the Department of Computer and System Sciences at Stockholm University in Sweden. His research interests intersect psychological signals, machine learning, and virtual reality. And he will present a small piece of his work entitled with Excitometer, yeah, that's a word. Software framework to integrate bodily signals in virtual reality experiments. So Luis, please take it from here.
Okay, thank you. Okay, hello everyone. Thank you very much. I'm going to present, that's correct, Excitometer. Let's start with a brief introduction. So let's talk about the importance of bodily data in virtual reality. So we all here know the importance that virtual reality has to simulate real life scenarios, and how clinicians and many researchers have used this amazing technology to study many psychological principles or physiological principles, such as user perception or the way how people interact with virtual environments. A common way to collect data from user studies is through self-reported measures, the questionnaires or the interviews that are conducted afterwards. But these are not always a reliable source of data. So the ultimate goal is to try to represent the dynamics, the specific dynamics that each person has while they are interacting in VR. And here bodily data can provide some extra information and hopefully enhance the design of virtual reality applications. So why bodily data? Because they can measure inner physical and mental states in a closer way. You can record them without any interruption during the interaction of the user with the virtual environment. And they don't have to exclude the self-reported measures, but they can also complement in the research that we conduct. Hopefully at the end, the goal is just to support more personalized experiences where VR systems can understand the underlying behaviors of one person and adapt to it. How do we collect bodily data? Then it's wearables. Luckily, we have a lot of wearables nowadays. However, there are some integration challenges between the wearables to collect behavioral data and the game engines that we traditionally use to develop the virtual environments. In addition, even if you were able to collect physiological data by yourself, it sometimes requires some expertise to transform that data into usable information. How do we interpret that physiological data? And the other challenge is, if we are doing experiments with VR and physiological data, we would like to do annotations, kind of to mark specific actions that are happening while you're interacting in VR, so you can use all this information together at the end of in a post-session analysis when you're working offline on your data. So for this reason, we have created the Excitometer, which is a software framework that allows developers, researchers, hobbyists to easily integrate bodily signals in custom VR applications, and specifically using the Unity game engine. The first step to design the Excitometer was to conduct an online survey asking potential users which were the requirements that they would like to have in such a platform. So we had 58 people among researchers, developers, and clinicians, and we elicited 6 requirements in total, but 3 key requirements were that they wanted to be able to observe the user's physiology in real time. The second one was to be able to let the virtual reality environment react to the changes that were detected in the user. For instance, if the heart rate was going up, then you can modify something in the virtual reality environment. And if the heart rate is going down, then you probably change something else to try to keep the person engaged. That would be like a basic use case. And the third one was to be able to conduct offline analysis. So this is the very simple architecture that we showed to the possible end users when they were conducting the survey, the online survey. But then this architecture was translated into this one when we finally implemented the software framework. The first stage of the architecture, the Excitometer, refers to the data collection component. So you have some wearable sensors that need to be connected to the Unity game engine and send the physiological data to be used by this in the virtual reality environment. The second one is one intermediate stage when you have feature extraction, then the physiological data, heart activity, in this case, it needs to be transformed into more meaningful metrics that could represent something more interesting in the end user. And the third part was the VR integration, that now it's all the core scripts that allow your virtual reality scene communicate with our plugin. In the data collection, we have developed through middleware applications, one for Android and another one for Windows. When you have access to heart activity, and specifically from the Polar H10 chest strap, we have made the software compatible with LSL protocol, because there are many wearable devices that are compatible with LSL protocol. So one of the ideas is to start expanding the near future with other devices that can provide meaningful physiological information. So on the right side, you have a screenshot of how the application looks like. So through that protocol, then you come back to Unity. You have a default scene. In the right side, you can see a traditional scene. It can be whatever you have in your virtual reality scene. And the Excitometer's plugin is going to provide this panel when you can see the heart information in real time. And you also have some sections where you can annotate and label specific situations of the environment. So here's a short example of how easy it will be to integrate the Excitometer. So you just have to add a couple of scenes that are included in the package, and then it will enable this panel where you can see heart information, and in this case are intervals, which is a specific feature that you can capture. And we also include an offline management scene that will be compiled also in the same virtual reality environment that allows you to load data from different users, choose the specific features that were captured, and also when you drag in the timeline, you can see screenshots of what the person was looking in the virtual environment while they were doing a specific task during that timeline. Then the first part of the evaluation had to do with the technical components of the excitometer. Something we wanted to assess at the beginning is if including real-time acquisition of physiological data from wearables in Unity was going to affect somehow the performance of the virtual reality application itself. So we compared the acquisition in Unity with the traditional software that is used to collect physiological signals, like the standalone software, but we didn't find any data loss between both scenarios. And the second one was the kind of the overhead of also doing feature extraction in real time. So we also didn't find any difference between the features that were captured with real time and the ones that you can calculate offline with normal Python or R script. The second part of the evaluation had to do with the validity of the data itself. So nowadays, all these projects that are using physiological data for psychological experiments, most of them use research grade sensors, which are quite costly. So we wanted to make sure that the wearable sensor was capturing valid data, or at least as valid as it can be to conduct quality research. So in the user study, we connected some users to both sensors, the research grade sensors and the Polar 10 chest strap, while they were doing an activity in virtual reality. And we compared the acquisition or the data that was collected in both of the systems. So the worst correlation that we got was 0.947, which means that all the data collection was more correlated than this value once you had the sliding window of the data related to both sensors. At the end of the paper, we provide a small use case example of just kind of depicting how these kind of tools could help to advance research in physiological computing, psychological experiments, or user modeling based on behavioral data. And for this, we used 4 videos publicly available, for 360 videos from the Virtual Human Interaction Lab of Stanford. And the users were measured in the heart activity while they were watching the 4 videos. 2 of these videos were labeled with a low arousing number, or considered low arousing, and the other 2 videos were considered high arousing videos. So we used the excitometer to collect this data, and we tried to come up with a preliminary algorithm that could interpret excitement level from the physiological data. This is an exploratory. This is just the first experiment we run here, and we plan to make this user study larger in the near future. But then this is just to show the capabilities of the tool. In conclusion, then we presented the excitometer, which is the open source software tool to integrate heart activity in existing Unity VR applications. Now we use the survey to elicit proper requirements among potential users, but it was designed or developed thinking of researchers, clinicians, and hobbyists that don't necessarily have a lot of technical experience to integrate these things in Unity. And the evaluation, we analyzed the data reliability, the sensor's validity, and we did a preliminary user study. And in the near future, we also plan to include motion trajectories with the excitometer, so you can conduct analysis combining both physiological and motion data in VR. And you can access the website if you want to know more details. We also have a public GitHub repository. And finally, I would like to provide some acknowledgements to all the researchers that were involved in this project and some of the funding institutions. Thank you.
Excellent. Thank you very much, Luis, for this very nice presentation. So please raise your questions, and there is coming the first one. So we'll read it out. It comes from Wolfgang Fuhl. Do you plan to integrate machine learning approaches for supportive annotation and tracking of marked regions, for instance, considering heart rate?
That's a great question, because that's one of the reasons why the excitometer was created. So we envision this tool as a first step to provide enough data collection that ultimately allows the design of machine learning algorithms, both for user modeling, and I guess also it can be used for data annotation if it's the goal. But that's one of the goals of my PhD project, actually.
Okay, so are there any further questions? Otherwise, I will have one. So considering, there's a one. So I will take this first. Do you have a plan to integrate eye tracking data into the platform as well?
We haven't discussed it, but the first thought is, since eye tracking is getting embedded in the VR devices nowadays, it shouldn't be that difficult already to provide some integration between the, let's say, the offline analysis module we have created with data that you can already capture in Unity. So the motion data can be captured from the trackers of the VR headsets, because there are already libraries intended to deal with the data from the headsets. If the headset includes eye tracking, then that data can also be kind of forwarded to the excitometer pipeline. And here we were addressing a little bit more the challenges of including data that is not natively included in Unity, or that you cannot easily embed in VR. So definitely, I think that eye tracking could be a part of the pool of data sources available.
Okay, so I would have a follow-up question there. Do you plan to integrate anything else? So beside from the eye tracking, anything else than heart rate? Because I think heart rate is a measure, but probably not the only one. It might be also strongly correlated to many other aspects you are not interested in. For instance.
Absolutely.
Yeah, please.
Sorry. We are working also with embedding or making it compatible with some BCIs. So some of the co-authors are working a lot with BCI, and we want to embed wearable BCIs, not like the ones that just take into account the sensors from the frontal cortex and not the ones that require all the wiring. So we are very keen on including also more physiological data. And that kind of is also the goal of making it publicly available, that if there is more interest from the research community to work on these kind of things, that you can just contribute to the repository, and then we can expand like the excitometer with a lot of interesting options.
All right, so I would say this brings us to the end of the session. Thank you very much again, Luis, for your presentation and for discussing all these questions with me. Before I will formally close the session, I would like to invite everyone to the GatherTown Q&A rooms. We are here on track A, so you will find all the presenters in their specific rooms in the sequence as they presented. So you will find, for instance, Luis in the room A5 in the Q&A room. So this brings me to a big thanks again to all presenters and all participants raising questions and discussions. And yeah, please, I wish you a very nice conference going on, and please don't forget the events this afternoon. Yeah, take care. Have a nice ISMAR. Thank you very much. Bye-bye.